I want to take a look at another symmetric circuit, and this time also again with dependent current sources, that's even a bit more complex. Now this is coming from a differential amplifier. In fact, actually a rather interesting differential amplifier with common mode feedback. In particular, a place where the common mode feedback is coming from a capacitor divider into sort of the up into these sort of current source nodes. And so it's kind of a very useful circuit, one I've used personally many times, and will be used quite a bit going forward. So it's a neat circuit, and it kind of illustrates all of the possibilities you get when you take sort of linear dependent source circuits, and what happens when I want to split this into a differential and common mode circuit, and what are the various pieces and parts of that solution. So I kind of want to work through this, and I think that what you'll find is that this is a kind of a fascinating circuit. Now there's another video that discusses a slightly simpler version of this as a differential amplifier. I'd certainly recommend taking a look at that one as well. But we're going to kind of start and go through this one sort of building all the way through this again. So given that, what we're going to be looking at is saying, all right, I've got this particular large circuit. We can see that it's symmetric, but two things you have to notice very carefully to notice its symmetry. One is that this resistor R0 can be split into two R0s. And that turns out to be two different R0s in parallel. So that does allow me to slice through this node and get some symmetry. This capacitor CW also can be split, but now I'm dealing with two different capacitors in parallel, which means two of them of the value of CW over 2. So that gives me that gives me those pieces, and that does allow me to kind of talk about a slice through the middle here. This actually is now two nodes of symmetry. And just to remind you that, remember what happens in nodes of symmetry for common mode circuits is it effectively gives me an open circuit because everything is well balanced, so at that node of symmetry there's no current that goes between it. Whereas when I'm looking at a differential mode circuit, that node is basically going to be held at ground or a fixed potential. And in a typical circuit where I always have DC pass to ground everywhere, it will always be 0. Only in a circuit where I don't have a DC pass to ground would I imagine that it wouldn't be 0, and then I have to find a way to be able to handle that in some form or approach. So, where do we begin in such a structure? We begin by trying to cut through the middle of this, and we actually can see that there is a differential mode circuit. Differential mode would mean these two voltages are basically being held at ground or at a fixed potential. And I'm going to call this one at ground with the differential mode circuit, saying that if I need to, it'll show up in the common mode circuit. We can look through this much more carefully, but we'll kind of start there to kind of keep it simple. And so for the differential mode circuit, what I would end up getting is basically this goes, V is at ground, which basically also means these sources disappear. It would also mean that this slices through the middle here, so this node basically gets stuck at ground, which basically means Vx is ground, which means these sources disappear. And so all I'm left with is this resistor R1 and this current source, and solving for basically for the output, which you could talk about here as being VA. And of course, VB will then be going in the opposite direction. Whichever way VA would go, the other one would go in the opposite direction. And so simply I'm going to have a GM and an R1. It turns out, given the values we have, that would give me a value of like -40. Pretty typical kind of analysis and approach you would expect there. The common mode half circuit, on the other hand, is a different discussion. And again, I cut it, but then it's going to mean the lines are going to be broken, and it's just going to be open circuits between them. And so that's what I'm getting in both cases. And so what you can see is I get the capacitor network. This is over 2. I see 2R0. I get these different current sources, resistor, and I get this additional structure. Okay. It is this part of the structure which this gets interesting. And the way you can think about it is, well, what is Vx? Well, I could talk about this going between this V out term and Vx is effectively going to be is basically a capacitive voltage divider. And so that we can clearly understand what that division would be, because it would be C1 over the sum of those capacitors. Okay, that works. There's also a charge at this node, and that is something that's extremely important to understand how we're going to put that, how we would look at that. By the way, this circuit definitely works all the way to pretty much, almost all the way to zero frequency. At zero frequency, there's always an interesting discontinuity if you go through these things carefully, but it goes all the way there. And so it's basically a circuit that you would see operating in the space. Okay, so what I would get then is an interesting voltage divider, and that would then say, take whatever this voltage is V out, and I divide it down. Well, that's now going to be the voltage that goes into Vx. And so that's a dividing down term. And so if I assume that the excess charge at Vx is 0, and that's an assumption, and you'd have to be told that ahead of time. You can always program that to something different, move that to something different, shift it, which then would add like an additional current here. But let's keep it at 0, just kind of keep the math simple for the moment. And therefore, I would get a divider, and what I would effectively end up seeing is that I would get basically 1 over GM2, CW over 2 plus C1 over C1. Well, for the values we have, that's actually going to end up calculating out to being 4 kiloohms. And this whole thing just looks like a resistor. Why? Because eventually, if this is a current source that's dependent on the voltage across it, it's going to be effectively just a resistor. And so that's what it'll often convert to. And so I'm seeing that, and then I'm seeing the R1, and so this is effectively a much smaller resistance. So I'm just going to be able to ignore the R1. Well, I can then sort of solve out for what V is and kind of get that whole solution there. And then given the parameters we have, V is roughly about half of the common mode input. I also then get the additional ratio for V and VB. And so eventually I find that VB is basically related to R over 4R VC. This R is now this 4K. And that's how I'm representing it. So it's basically going to be that R over the 2R0. Again, this is the R. It's sort of an effective resistance as we're looking at the analysis. And we find out we get a very, very small gain as a result, which is what we'd expect for a common mode gain to be very small and for the difference to be quite large. And it's interesting because if you were to look at the previous video on this, the difference between this was significant, but this is even more. And if you're looking at this closely, this is a case of I'm getting common mode rejection because of what's going on in this differential pair stage, as well as what's going on in the common mode feedback. So it actually turns out to work. You actually sort of get double levels of sort of getting rid of the common mode structure, so you get a really good differential gain. And this is kind of how you might imagine such a structure.